the FAQs. What exactly is the Q value? This was a frequently asked question. If you had watched the discussion video from last week, I discussed that in detail about what is the specific point about a Q value. So Q values are cumulative rewards. And this is different from the immediate reward that is represented as R in the homework problem. I will show what exactly a cumulative reward and an immediate reward is in a short bit, but this would be the definition or a textbook answer of what a Q value is. Q value is. And the next question is, how is cumulative reward different from immediate reward? Again, going back to the previous answer, cumulative rewards are obtained for performing a state action pair multiple times and receiving rewards each time you perform this action. So in a textbook sense, cumulative rewards are rewards you accumulate by doing a state action pair multiple times. That is, immediate rewards are obtained for performing an action once. Cumulative rewards are rewards you accumulate for performing an action multiple times. We want to see it with an example. Let's go to the experiment discussed in lecture about an animal being trained in a cage for 10 days. For 10 days, it just stays in the cage, does nothing. It has two options in front of it. It could either press a button or not press a button. For 10 days, there's no difference between pressing a button or not pressing a button. Doesn't matter. It could just do whatever it wants. So the start Q value after 10 days for this animal would be Q of animal in cage and pressing a button, the Q value is 5, and animal in cage and not pressing a button, the Q value is 5. Both of them are going to be the same. There is no difference. That's just a starting Q value after it's been trained for 10 days. On the 11th day, the animal has two options in front of it, which is it can either press a button or not press a button, right? So if it presses a button, it receives some juice as reward. And let's say we indicate that reward by a value of 2, just a numerical value that we attach to it for easy understanding of the problem, and a reward of 0 for not pressing a button, because if it does not press a button, it does not receive any juice. So on the 11th day, this animal in the cage presses a button. Let's say it because of the fact that the Q values are the same, it could either press a button or not press a button. So let's just assume that it presses a button in the first iteration. And if it presses a button, then the reward that it gets is 2 here. And the max Q value in the next state action pair, because this is a terminal state, is 0. And the alpha value as defined in the lecture is 1. So if we plug all of these values in the equation for Q value update, we get a Q value of 2. And what does this mean? This means that after one iteration, if on the other hand, the animal does not press the button, then the Q value again it's 5 and the reward is 0 because there's no juice, the reward is 0. The max Q value is again 0 and the alpha is 1. And if you plug everything in the equation, then the Q value becomes 0. So this is after one iteration, right? So after one iteration, that is after one trial of the animal either pressing a button or not pressing a button, you see that the Q values are updated like so. It becomes a 2 and a 0. Okay, this is after one iteration. So now if you see the Q value of either pressing a button or not pressing a button is not equal anymore. It has changed from being equal to pressing a button, receiving a higher Q value. Whereas the rewards are slightly different if you look at the problem definition, right? So what this indicates is that even though the immediate rewards are going to be different, the cumulative rewards are what matters in choosing long-term goals. So after iteration 2, the animal is, of course, going to choose the option of pressing a button, because pressing a button now has the higher Q value. With this higher Q value, if you plug in all the values and update the equation, the Q value again becomes a 2, which indicates that this is the real or the true Q value of the problem. And so after iteration 2, the Q value of the animal pressing a button becomes 2. So now if you look at this problem, the animal just with one button press has realized that, hey, if I press a button, I am getting a reward, and this reward is going to get cumulative for the animal, and it's going to be a rewarding experience for the animal to continue performing the same action. So it has essentially updated its Q value in such a way that it prefers the action that constantly provides it with a reward. This example could be extended to the example of classical conditioning, where the dog salivates on seeing a, or rather dog salivates for a bell ring, which we saw in discussion section last week. And if you see the start state of this, or the Q values here, you see that the start state, bell rings, dog intrigued, no bell, no treats, and so on and so forth. And after day 1, iteration 1, the Q values become this, like here. And after day 20, that is iteration 20, the Q values become like this. So it just indicates that each of these iterations are just an action being performed multiple times over several days or over several iterations, several hours or several actions. So you do the same action multiple times. That is what is referred to as iteration in your homework or your assignment problems which you practiced. So what is the prediction error in all of this? So if you look at the equation for the Q value update, you see a small portion there, which is referred to as the prediction error. And look at all the terms in the prediction error. You have the reward, you have the max Q value of the next state action pair, and your current Q value of the state action pair. So what exactly does this give you? So if you look carefully, if a dog is intrigued because of the fact that a bell rings, a dog is intrigued, that is its state. So how do you update the Q value of a start state and bell ringing state action pair? So the state action pair is start state and bell rings. So you reach here. So how do you update this Q value? You update this Q value by including the reward of being in a particular state and by considering the maximum Q value of the next state action pair, right? So if you look at this carefully, from here, the next state action pair, which the dog would like to have, is the treats being given, because it always has the highest state action pair. So the dog knows that when the bell rings, and if it is intrigued, it is definitely getting a treat. That is what classical conditioning does, right? You condition the dog with a bell ring because you are saying that whenever a bell rings, I am giving you a treat. So the dog automatically assumes that, hey, this one is having a high Q value, and if I reach this state, I'm definitely getting this. So the dog is not salivating because it's intrigued. The dog is salivating because it starts in the start state and chooses the action of bell rings, and it's intrigued. And when it's intrigued, it knows that it's going to be given a treat. That is why it's salivating. And where does the prediction error comes in here? The prediction error comes in the fact that the dog is receiving a positive error here. So the prediction error is positive. So that's like a positive reward. That is what the prediction error does. And this reward could be negative as well. So negative rewards or rather negative errors or unexpected negative things that might happen. In this case, in classical conditioning, this is a positive error. That is a prediction, positive prediction error. The next question is, how does alpha affect the prediction error? So if you looked at the solution for the assignment last week, you would have seen this graph here. So in this graph, you can see that you have different alpha values, 0.2, 0.5, 0.7, and 0.9. The 0.9 alpha values, this one here, the purple line. If you see, the true Q value is 3 for the state action pair of UF exam and open textbook, which is the example we saw in the assignment last week. So this true Q value is 3, and for an alpha value of 0.9, it just almost immediately reached the true Q value. And as the alpha value keeps reducing to 0.7, 0.5, and 0.2, it keeps taking more and more time for the true Q value to be reached. So alpha value is essentially the learning rate that dictates how soon you reach the true Q value. There's no specific solution as to what an optimal alpha value is. It totally depends upon your problem statement. It totally depends upon what you're learning, for example. You could equate it to your learning rate of, say, for example, a person learning a guitar. Is the person going to be really fast and just learns everything quick and going to be making a lot of errors in the way, or is the person going to be really slow and steady and going to go through all of the processes and learn it slow? So you could be fast, but if you are fast, it's not a guarantee that you will reach the right Q value all the time. Here, because this was a toy problem, you always reach the right Q value, the true Q values, but it's not always the case. If you're really fast, the graph here for reaching the true Q values might actually be something like this. So you might never reach the true Q values if your learning rate is too fast. But if your learning rate is slow, or rather slow enough, you would take really long to go to the true Q values, but you would eventually reach it, for example, like this, right? So if your alpha rate is really high, you might go all over the place and not converge at the true Q value. So it's a fine balance that you need to have here. So the alpha value essentially weights the prediction error and shows you how quick or how slow you reach your true Q values. Okay, the next question was, if the R value of something is low, it doesn't mean we stop doing it. Why is that, and how does it happen in real life? So I'm assuming that the person who asked this question asked it with the idea that if a reward is low, we still do that. It's not we stop doing it. But why does it happen in real life? So as I said before, R is an instantaneous reward. So we don't look at instantaneous rewards in performing specific actions. For example, even in this example, if you see here, if for choosing which action to perform, sorry, not this one. Wait. Oh, okay. So thinking about the assignment problem from last week about opening Netflix or opening a textbook. So you don't choose to open your textbook or open Netflix based upon the reward that you get for performing either actions, but rather you perform the specific action from a given state based upon what the Q values are, right? So you perform any action based on the cumulative rewards, not on the instantaneous reward R. That is why even when an R value is really low in real life, we still perform that action because the cumulative rewards are high. For example, exercising every day is not the most pleasant experience for most people because it is painful. It is not pleasant after you finish exercising. You're tired and you're exhausted. And the immediate reward, the instantaneous reward, is almost always going to be negative, right? But what is the cumulative reward for performing exercises every day? You're going to look fit, you're going to be attractive, and you feel good in the long run. That is the cumulative reward, which is way better than the instantaneous reward of performing an exercise. So that is why you still do or still perform exercises with which probably have a low instantaneous reward in real life, but have a really high cumulative reward. Okay, next question is, how did we deal with finding Q values as children when we did not have any prior knowledge or experience? So like the person who asked this question has specified, we indeed did not have any prior knowledge or experience when we were kids, but we did it with this so-called explore and exploit idea in reinforcement learning, where you explore things and find their rewards and their cumulative rewards. If you perform good things, or rather, if you perform pleasurable things, you get positive rewards. And if you do things that cause you pain or agony, you get negative rewards. And you accumulate these as cumulative rewards. And over a period of time, you use these cumulative rewards to update your Q values. And based on that, you obtain knowledge about the world, which you can assume in a Bayesian sense as priors that you have about the world. You sometimes are born with priors, sometimes, or sorry, for some cases you're born with priors. For example, the sun comes from above, as we saw in the Bayesian learning framework. So those things are priors you have. But then for actions you take, for example, how do you know that you should not touch fire, for instance? Someone tells you, or you have touched hot objects and you know that it's not a pleasurable thing, it's a negative feeling. So you updated your Q value saying that my Q value for touching fire is really, really low. If there is a start state and if there are two options, touch fire, don't touch fire, then your Q values initially would be 0 for both. And you update your Q value the very first time you touch a hot object or a fire. And the Q value is going to be really, really, really low for touching fire, that you never ever touch fire again. So that's how you update your Q values in real life. Next question is, why do we do this thing for multiple iterations, and when do we stop it? Or how do we know how many iterations to perform? So this multiple iterations are just a proxy for doing something multiple times in life. You could do a thing several times. You could do an action multiple times. Like I was giving you the example of performing exercises. You do your regular exercise, you work out every day. It could be equated to you performing an action. Start state, you're having two actions from the start state: perform an exercise, don't perform exercise. Here by exercise, I mean like the workouts. Do a workout, don't do workouts. Those are the two options you have. And you're not going to just perform like, say, 7 iterations or 8 iterations of workouts, right? That is, you don't work out for 7 days or 8 days and just stop working out. You keep doing it over and over again, right? You don't stop it. There is no true Q value for performing a workout. Of course, there might be a Q value where like you keep performing workouts every day and you know that yes, performing workouts is the best option in the long run. In the cumulative reward sense, performing workouts are the best. So how many iterations did you perform to know that doing workouts are the best way for you to stay fit and stay healthy? I would not know the answer. I don't think anyone would know the answer. So that's how we would say, or we would know how many iterations to perform in real life. The next question is, what is the gamma value for the discounted reward, and why was it ignored in the homework problem? So if we look at the equation for the gamma value, okay, I put in the wrong equation here. The gamma value should go here. So here is the gamma value. Okay, that is not really clear. So the gamma value is supposed to be here. So the gamma value weights, and here's the alpha value. So for now, let's not consider the alpha value, but the gamma value is supposed to weight the max of the Q value of the next state action pair, right? So this is essentially equivalent to what we saw here. in rationality. How did we weight the discounted reward for something you get in the future? If you get $999 now or $1,000 in a month, based on your gamma value, you decide what is the utility of your future reward or what you get in the future. Similar, it's exactly the same here. So here you have a gamma value weighting the max of the next state action pair. So this literally translates into how much do you factor in future rewards or future cumulative rewards in your decision making. If your gamma value is really high, if your gamma value is, say, it's on a scale of 0 to 1, and if your gamma value is 1, it means that you place so much emphasis on your future cumulative rewards. But if your alpha value is really low, it means that if your gamma value, that is the discounted reward. So if your gamma value is really low, it means that you don't place much emphasis on your future cumulative rewards, but rather you place a lot of emphasis on your instantaneous reward, because the lower this value is, if you make gamma as 0, it means that this whole term disappears. Right? So if this whole term disappears, what is the only thing that is left? Only the instantaneous reward and your current Q value. If your gamma value is 0, that means that you are an extremely impulsive person who does not think about the cumulative rewards of the future. You just think about your instantaneous rewards, right? So that is what gamma does. That is your discounted reward. These two are equivalent. It is essentially the same, telling you how much weight you give for your future cumulative rewards. And the reason that it was ignored in the homework problem was because was just to simplify the idea of the whole Q-learning algorithm, and also the fact that the problem was a toy example and doesn't matter if gamma value is given there or not. It would not have made much of a difference until you actually calculate the iterations for, say, 10 or 20 times, at which point gamma would have started making sense. But gamma was ignored for that very simple reason that it would have been cumbersome for you to have calculated it by hand. But in real life, gamma is an extremely important term which weights the future cumulative rewards. Okay, the next question is gut feelings. So how is the Q value related to gut feelings? And this was explained with the example of I have a gambling task, and putting it in terms of this toy example again, you have a start state and you have two options. You have a good deck. You could either choose a good deck or a bad deck. And if you choose a good deck, the reward for it is 2. And if you choose a bad deck, the reward for it is -2. Initially, you don't have any idea about which deck is a good deck or a bad deck. So you start with a random Q value, which is 0.001 for both, which means that you could have chosen anything, any option at any point of time initially during the first few iterations. And say after the first iteration, you have, that is after drawing the card once, your Q values probably would have updated to this. And after drawing it for 20 times, your Q value has updated to this. Still, it has not settled down at any one point. So you're still doing it. And after 100 iterations, that is after 100 trials of, okay, there is a typo here. This is not iteration 4. This is iteration 100. So after 100 iterations, that is after 100 times of drawing the cards again and again, you realize that drawing cards from the good deck results in a much higher cumulative reward compared to drawing cards from a bad deck. So this means that your gut feeling, that is your Q value, the true Q value, has increased so much for drawing from a good deck that you instinctively feel so. So that's your gut feeling. Your gut feeling on, say, for example, touching fire, your gut feeling is going to be just don't touch it. It's harmful because your Q value is so high for not touch, sorry, Q value is so low for touching fire that you don't touch it. Similarly, when you do a task such as this Iowa gambling task, where you know for sure that drawing from a good deck is going to give you money, your gut feeling or your instinctive impulsive response is going to be really high for drawing from that specific deck. And people with ventral medial prefrontal cortex damage don't have this gut feeling because of the fact that, or rather, it's the other way around. People with VMPFC have shown to have bad performance on Iowa gambling task, and as a result of this, it is inferred that the VMPFC is a nodal region for storing these Q values, that is cumulative rewards in the human brain. And that's where the cumulative rewards are stored. So these are all inferential knowledge of how humans store these rewards and how long-term learning occurs, which comes to our next question. What is the point of all these things? What is the purpose of the whole thing? A very simple response is that the purpose of the whole thing, whole Q learning algorithm, is learning. How does human learning happen? That is one simple response that I can give for what the purpose of this whole thing is. And what do I mean by learning? So if you think about an Iowa gambling task, for example, it literally tells you how you learn to choose a good deck from a bad deck. Where is all of this learning encoded? How does this learning happen? How are the rewards encoded? How are you getting your rewards? How are these rewards accumulated together to form cumulative rewards, and so on and so forth? So every life example can be translated into such a kind of a problem. And that is exactly the purpose of this whole thing, trying to learn an algorithm that could explain how human learning and cognition happens. Okay, I think that's the end of it. I hope it clarified some questions at least, but feel free to leave comments about any other questions that you might have. Thank you.